Students, today we will start with the new unit, that is unit number 4 of structural analysis 1. So under this unit we will going to study the two major element or the structural part, that is a column oblique strut. Okay, so in engineering the column is also called as a strut, and the analysis of two hinge arches. Okay, so basically this unit contain 13 marks. Okay, so out of which one question may be asked from column and strut and one question may be asked from analysis of two arches. So let us start with the first topic, that is column and strut. So the basic of the column and struts are as follows: any members which subjected to the axial compressive loads. Okay, axial compressive load is called as a column or a strut. Okay, so we know that in a building or in a structure, the building is subjected to various types of forces, and basically there are a number of forces which are acting on the structure. It may be a tensile force, it may be a compressive force. Okay, so whatever the compressive force which is acting on a member, or the member which is responsible for taking that particular compressive load, is called as a column. So in a structural geometry, the column or strut, basically strut may be defined in the field of the steel structures, because in a steel structure the column is not available, they are called as a strut. Okay, so any member in a steel structure, in any member which contain or which carries the compressive loads, is called as a strut. Okay, so second is the vertical member subjected to the axial compressive load, that is column. For example, the pillar of the building. So this is the best example. Now next is an inclined member subjected to axial compressive load, is called as a strut. These are called as a strut. The strut may also be a horizontal member. Okay, then load carrying capacity of the compression member depends not only on its cross sectional area, but it also depends upon its length and the manner in which the end of the columns are held. Okay, so the end conditions of the columns are most important. Okay, by which we can say that the compressive loads is acting like that. Okay, now next is the equilibrium of the column, may be stable, unstable and neutral. Then the critical and crippling or buckling loads. So load at which the buckling start is called as a critical buckling loads or crippling loads. Okay, then the column is said to have a developed and elastic instability. Okay, so one thing you must understand that before starting this topic, that the column is a compressive member. First important thing is that. Second thing is that the column is not subjected to any shear force or any particular kind of a stresses. It may subjected to the torsional buckling and inelastic buckling. Okay, so classification of columns. Okay, so what are the types of column? Let us see. According to the nature of failure, it may be defined as short column, medium column and long columns. So let us see short column. So these columns are the columns whose length is so related to its cross section that failure occurs mainly due to the direct compressive stress only, and the role of the bending stress is negligible. Second is a medium column. The medium column is one whose length is so related to its cross section that the failure occurs by the combination of the direct compressive stresses and the bending stresses. Okay, then the long column. So the long column whose length is so related to its cross section area that failure may occur mainly due to bending stresses, and the role of the direct compressive stress is negligible. Then there are two theories associated with the failure of this buckling column. First is the Euler theory and second is the Rankines theory. Okay, so Euler and Rankines are the two scientists who has worked in the particular field of this buckling of column, and has developed two standard equations which are universally accepted, and these equations are most commonly used to calculate the buckling of the column. So let us see this theory and their derivations and their formula step by step, because in examination also you may be asked to solve one particular derivations from these particular theory. Okay, now Euler theory, columns and struts which fail by the buckling may be analyzed by the Euler theories. Okay, so there are the certain assumptions on which this theory is depend. The column is initially a straight, cross section is a uniform throughout, line of the thrust coincide exactly with the axis of column, then the material is homogeneous, isotropic, and the shortening of the column due to axial compression is negligible. So these are the basic assumptions by which this theory is depend. Now there are the cases. Okay, so we know that by the definition itself, the end conditions of the column is most important. So based on the different end condition of the columns, the various formulas are generated. The first important case is both end hinge. Suppose this is a column. If you see the diagram, this is a column, and if the axial compressive force is acting in the form of P, this is P. Okay, so because of this external compressive force, the column will try to buckle in this direction. Okay, this is a Y, this is the axis of buckling. Okay, the Y axis is there and X axis is there, and the column is try to buckle in horizontal direction. L is the effective length of the column. Okay, so this is a particular cases which is applicable. So when both the end is fixed, so the derivation EI d square by dx can be calculated as is equal to m is equal to moment, and if you apply the moment here, it is equal to minus p, this is minus p into y, minus py is the equation. So this is the equation will be generated as per the Euler theory. EI d square by dx, okay, is equal to m, and m is nothing but minus py. Now further we can write it as EI d square y by dx square is equal to m is equal to minus py. So this equation can be written as d square by dx square plus alpha square y. Okay, so alpha we are taking as a constant is equal to 0, and where this alpha value can be taken as p by ei. P by ei is the alpha square value. Okay, now the solution of this equation, okay, this is a standard derivative equation. If you see that, so the solution can be defined as in terms of y is equal to a sine alpha x plus b cos alpha x. Okay, so this is a simple equation, simplified equation of this particular derivative form. Okay, so now put the various conditions. We are having a two ends, that is x end and y end. This is a x, particular distance x, where the buckling occurs at the center, and this is a y end. So we will see, and we will put the particular conditions here, and we will see what are the effects. So at x equal to 0, y equal to 0, so b will also equal to 0. When we put x and y equal to 0, x and y equal to 0 here, so then b is equal to 0. Then at x equal to L, if x equal to L is considered, overall length is considered, and if y is equal to 0, then a sine alpha L will be equal to 0. Now if a is also 0 and y is 0, then for full value of the load, then there is no bending. So therefore sine alpha L equal to 0, or we can say that alpha L is equal to pi. Okay, because sine value is considered as a pi, as a least value, or alpha is equal to, we can simply write it as pi by L. So Euler-Kirping formula is for PE is equal to alpha square EI, that is equal to pi square EI by L square. This is the generalized equation of the Euler-Kirping load. Okay, so this particular formula is applicable only when both the end are hinged. The column which is having both the end are hinged, in numerical itself you are giving the condition that if the ends are hinged, then you will going to use this formula for that particular case. Now second case is one end is fixed and other end is free. Suppose this one end is fixed, bottom end is fixed, and other end is free to move. Okay, now if in that case we apply the axial force P at a distance, particular distance A is created, and we are interested in calculating the bending because of that particular load. So what will be the condition of the equation, derivative equation? It will be equal to EI d square by dx is equal to m. M will be there, m is the moment will be formed, but here m will be what? P into a minus y, because a is the overall horizontal length and where we are calculating a minus y, that is the net value we are interested in. So p into a minus y, this value we have to consider, that will be equal to pa minus py. Okay, now again we can write it as d square y by dx square plus alpha square y is equal to p into a divided by ei, where again alpha square can be considered as p by ei. Okay, now the solution of this, okay, derivative will be equal to solution of is given by y is equal to a sin alpha x plus b cos alpha x plus this additional value will become here pa divided by ei alpha square. Okay, so again a sin alpha x plus b cos alpha x, it can be written as a. Now put the conditions at x equal to 0, y equal to 0, so ultimately the equation become b equal to minus a. And again when x equal to 0, dy by dx equal to 0, so here the condition is a alpha cos alpha minus b sin alpha cos alpha is equal to 0, where a is equal to 0. Again y is equal to minus a, okay, y is equal to minus a cos alpha x plus a, that is equal to a 1 minus cos alpha x. Okay, now third condition is when at x equal to l, y equal to a, the condition become a is equal to a 1 minus cos alpha x. Again cos alpha l is equal to 0 or cos alpha l equal to pi by 2. So therefore the value of alpha can be taken as pi by 2l. If you remember, in the last case we are getting the value as alpha by pi by l, but here we are getting the value of pi by 2l. So therefore the equation become alpha square ei, and we know that alpha square value, so we have to put that value pi square ei by 4l square. So this formula is applicable when one end is fixed and other end is free. Okay, now next case, that is the fixed both the end, if top and bottom both the end are fixed. Okay, now in that case the column will not going to restrain in this particular top and bottom side, but it will going to change its bending position exactly from the center, and the moment will be developed at top and bottom because of the fixity. Okay, so here in that case what will be the generalized derivative equation? ei d square by dx square is equal to minus p into y is there plus m will be considered. Already moment will be there, p into y, but along with that the moment will be formed, because at fixed support we know that the moment will be acting. Okay, so here the equation become ei d square by dx square is equal to minus py plus m. Now again d square y by dx square plus alpha square y is equal to m by ei. So where alpha is equal to again what we are considering, p by ei. So finally the derivative equation will become y a sin alpha x plus b cos alpha x plus m by ei alpha square. Okay, so we can generalize this equation and can rewritten as a sin alpha x plus b cos alpha x is plus m by p. Now put the various conditions. First of all, x equal to 0 and y equal to 0. So in that case this equation become b is equal to minus m by p. When x equal to 0, dy by dx equal to 0, in that case a cos alpha x minus b sin alpha x is equal to 0 or a equal to 0. So therefore y is equal to minus m, this equation minus m by p, cos alpha x plus m by p is equal to m by p 1 minus cos alpha x. This is the equation. So finally in that case here also we will get the final answer as alpha is equal to 2 pi by l. Alpha equal to this constant is equal to 2 pi by l. So Euler crippling equation become alpha square ei, that will be equal to 4 pi square ei by l square. Okay, so this is the third condition. Now the last condition is one end is fixed and other end is hinge. Okay, so in that case let us see what will be the changes. Now here one end is fixed and other end is hinge position. So we know that whenever the hinge position will be there, one vertical and one horizontal reaction will be formed. So because of that contribution of that particular reactions on the top, what will be the effect or what will be the changes in the derivative equation? Let us see. Ei d square by dx square is equal to minus py as a moment will be there plus r into 1 minus x will be formed. L minus x, sorry, not L, this is r into, this is r is there, this is overall length L is there, so r into L minus this x value we have to consider, this x value, so L minus x we have to consider. So this additional term will be formed because of when one end is fixed and other end is hinge, because at hinge support two reactions will be formed. Okay, now Again, this is the generalized derivative equation. We have to consider alpha square is equal to p by ei here also. Now this is the most common solution of this derivative equation: a sin alpha x plus b cos alpha x plus r l minus x by ei alpha square. Now again, when we put the equations, when we put the various conditions and condition at x equal to 0, y equal to 0, then b will becomes minus rl by p. Again at x equal to 0, dy by dx equal to 0. Here we will get a cos alpha x minus b alpha sin alpha x minus r by p equal to 0, or we can rewritten as a equal to r upon p alpha. Okay, so finally what we are getting, the value of alpha here 4.49 by L, 4.49 by L, and then finally the crippling load will become P is equal to alpha square EI, that is finally equal to 2 pi square by EL square. Okay, so this is the 4 basic condition we have seen. Okay, so you must remember at least the formula of that particular PE. Okay, what are the end result of that particular value of the Euler crippling load, you must understand it. And if your theory exam will be there, okay, university theory exam will be there, then in that case you will have to solve at least one, or you have to derive at least one end conditions out of these 4. Okay, or else if MCQ based exams will be held, then in that case you have to remember at least these 4 PE values of that particular 4 standard cases. That is, one end is fixed, other end is free. Okay, both the end hinge, one free, one one hinge, one free. Okay, one fixed, one hinge. These cases you must understand. The formula of that same you must understand. Okay, because based on that formula only you are expected to solve the numericals. Okay, now let us see some terms. Equivalent length. What is the meaning of equivalent length? So Euler load can also be expressed as a PE. Okay, PE can also be expressed as PE, which can be defined as pi square by pi square EL EI by L effective square, where L effective square will referred as the equivalent length of the column, which taken into account the type of the fixing of this end. Okay, so this equivalent length can be considered based on the different end condition. If both the end hinge, then L effective can be considered as L. Now if one end is fixed and other end is free, then in that case L effective may be taken as 2L. Then again, if both the end is fixed, then it can be taken as L by 2. If one end is fixed and other end is hinge, in that case it can be taken as 1 by root 2. Okay, L by root 2. So this is the end condition of the effective length. Okay, so in that particular formula itself, here L effective, you have to put the condition based on the end boundary condition of the column. Okay, then limitations of the Euler formula. What are the limitations? Okay, so assumptions is that the struts are initially perfectly straight and the load is exactly axial. But if you see in actual practice, the stress may be acting as an inclined member or the horizontal member. So in reality it can't be a perfect member. Okay, and load cannot be an exactly axial load. It cannot be acting exactly at the axial point. It may change from its original positions. Okay, so this is the major limitations of this Euler formula. Second is, there is always some eccentricity and initial curvature is present. Then in practice the struts suffer a deflection before the crippling load. So this is also a very very important defect of the particular case. Okay, now let us see. This is the critical stress. We can also calculate the critical stress. Okay, so this formula is pi square E divided by L effective by K square. So this L by K is most commonly called as a slenderness ratio. And in examination also you may be asked, in Viva also, what is the definition of the slenderness ratio. So whenever the topic of column is coming, you must understand the basic technical terms related to column, that is the slenderness ratio. So slenderness ratio is nothing but by definition as it is the ratio of the length of a column and to the radius of the gyration of its cross section. K is the radius of gyration of the cross section. So here slenderness ratio can be written as L by K, okay, and the radius of gyration Kx of the area about the axis can be defined as K square A. So here Kx can be written as under root of Ix by A. I is the moment of inertia about x axis and area is equal to area of the cross section of the column. So this is the most common equation, okay, a formula which is applicable for the slenderness ratio. So this was all about the Euler's theory. Now let us see the second theory, that is the Rankine's theory. It is called as the Rankine formula or Rankine-Gordon formula. So what are the assumptions of this particular case? Let us see. Euler formula is only applicable to long columns for which L by K ratio is larger than particular value. Also doesn't take into account of the direct compressive stresses. Thus the for column of the short member medium length, it does not provide the accurate result. And Rankine forwarded the empirical equation. Okay, so this is the modified equation of the Rankines. 1 by P is equal to 1 by PC plus 1 by PE, where P is the Rankine crippling load, okay, and PC is the ultimate load of the strut, which can be taken as sigma u into A as a constant material. Then 1 by P is the Euler crippling load, okay. So he has taken or he has formed one particular equation which is applicable for the shorter column, and along with that he has also considered the formula for incorporated the formula of the Euler bucket load, okay. So for the short column PE, this is PE is a very large, and therefore 1 by P is small in comparison with 1 by PC, okay. Now for long column P is very small, and therefore 1 by P is quite large in comparison with 1 by PC. So therefore the crippling load is practically equal to P, okay. So this is the generalized equation. We can rewrite as the equation as 1 by P is equal to 1 by PC plus 1 by PE. Now if you rewrite this equation, it can be written as 1 by P is equal to P plus PC by PCPE. Now if you solve this particular in a proper way, now you will get the finally the value as sigma CA divided by 1 plus sigma C into AL square by pi square E A K square, okay. Then again in generalized form it can be written as P is equal to sigma CA divided by 1 plus alpha in bracket L by K square, where sigma C is the crushing stress, as A is the Rankine's constant. A is the Rankine's constant, A, which can be written as sigma C by pi square E, okay. So again this is the generalized equation by which you can easily calculate the Rankine's load, okay. And here only you must remember that this sigma C value can be calculated, okay. It can be taken as sigma C by pi square E, okay. So this Rankine formula for the column with other end conditions will be equal to this formula, you must understand, okay. So P is equal to sigma CA divided by 1 plus alpha 1 plus A in bracket L effective divided by K the whole square. So this is the most generalized equation which is applicable, okay, for the long columns, and this is also called as a Rankine's crippling loads, okay. So this was all about the basic theory which is related with the column and strut. Today we have seen the two basic equations. One is Euler equations and second is a Rankine's equation, which both are applicable for calculating the critical or the crippling crushing load of the column, okay. So in next lecture we will going to start some numerical based on the same, okay. So thank you very much for your kind attentions. Thank you.